So we continue into fluid statics. It's a lot like the whole class you had of statics. So hopefully there's a lot of overlap from what you've been exposed to. We've covered a lot of material, but now we need to move into other material. Even last time we went down as far as curved surfaces. That's a little different than submerged planar surfaces. So we covered the submerged curved surfaces last time. So a water trough of semicircular cross-section of radius 0.6. So if it has a radius of 0.6, it has a diameter of 1.2. The diagram seems to be consistent. Consists of two symmetric parts hinged. Here's the location of the hinge at the bottom. The two parts are held together at the top by a cable placed every 3 meters along the length of the trough. You try to look down the length of the trough, maybe sketch it, get this perspective. There's the trough, there's the length of the trough, and every 3 meters is a cable, a cable, a cable, a cable, a cable. And so the distance between here and here is 3 meters, like the distance between there and there is 3 meters. So the cable has to support a length of 3 meters of holding it together, the tops together, okay, of the trough. Calculate the tension in each of those cables when the trough is filled with water. So the trough is filled to the rim with water, okay? So because it's symmetrical, what we'll do is we'll cut it in half right through here. And we'll draw a free body diagram. You can draw a free body diagram of the water only. You could draw a free body diagram of the water plus the trough itself. So if you cut with the, where you're going to draw the boundary, if you cut right in here, I really need to know the pressure that the wall, or the force, the action-reaction between the water at the wall and the wall on the water. True? What I'll do is I'm going to cut through here and come outside through the air. So you come outside through the air, and then we cut through the cable. But we're cutting right through the water as we're going down, and then we cut right through that hinge. So what's our free body diagram look like? It'll be some section that looks like this. And what type of forces do I have? Well, I have a tension in the cable. That's what I want to calculate. We have air, so there's really negligible pressure in the air. We cut through the hinge, so we have some, let's call hinge point A, ace of X, and I'll just put ace of Y like this, ace of Y. All right. Do we have any other forces that need to be on this free body diagram? The pressure, that's right. So let's go ahead and put our pressure in. It's a hydrostatic pressure. And so we're going to replace that distributed hydrostatic pressure with the singular equivalent force, and that a single equivalent force will be probably like that at that location. We'll call it F of R. We can calculate the magnitude of F of R and the location where F of R should be applied. Why not go ahead and do that right now? What is the height at which F of R is applied from point A? 1/3 of the radius, and that radius was 0.6 meter. 1/3 of 0.6. 0.2, is it 0.2 meters? Or 0.4 down from the top. Okay, but 0.2 up from A. All right. Now, is there any other body or surface force that I need to include in this free body diagram? The weight of the water. So this is where I want to know where I want to put some weight into the system. Should I put it at a distance maybe a third, 0.3, 0.3, put it right there, put the weight down? Or should I put it at a different location? First clicker question. The weight of the water, I'm going to figure out the magnitude of the weight in a minute. But should I put it at a location 0.3 down and 0.3 down? You know, is that how I'm describing that location? And if you click A, you say yes, that's where you should put the weight. Or B, no, that's not the correct place to put the weight for that water, for that diagram as shown. All right, so there it is. So most of us said no, and that's correct. It's no. So how do I find the exact location of where I put the center, the weight, which is going to be the center of mass or the centroid? I got to do some calculus, or I go and I look in my statics book or my dynamics book, or even in my fluids book, and I look for certain cross sections. And some textbooks will actually have a little diagram. They'll have the y-axis, they'll have the x-axis, and they'll actually put in a quarter of a circle. But this one, clipped out of your textbook, puts in a semicircle, half of a circle instead of a quarter of a circle. Okay, well, where do you think? Well, first of all, what does this little symbol mean? The centroid. It's the center of mass or the center of gravity or something like that. CG sometimes, center of gravity. That would be for a uniform density material over that area. Okay, so that's what we're interested in. What is the distance up from this bottom axis? The distance up is 4r over 3 pi. Yeah, if we had time, I'd get out the old calculus and do the integral and prove it, but I'll trust it. Okay? Well, for this case, how much do I shift over if I do a quarter circle? I know how much I shift up if I do a half a circle, but how much do I shift over? Because I really want to find that location. Yeah, the same. You have to, the professor never told me exactly the same. Well, symmetry and logic says it's going to be the same. Okay? So it's going to be shifted over as well as shifted up by the magnitude 4r over 3 pi. Let's jump back now to the problem. And so this location right here is going to be 4r over 3 pi. Go ahead and get your calculators out if you have them and tell me what is numerically that value. I think it should be less than 0.3. What is r? R is 0.6. And let's get it to 5 digits, 5 significant digits. So 0.46. Five. 465. Good. We have it to 5 digits. Thank you very much. So you see, it is a little less than 0.2. I mean 0.3. It's in the 0.2-ish range, 0.25 range. Okay. So now that's where we put the weight, acting downward. Now I have, let's summarize. I have T for tension. I have F of R for the hydrostatic resultant force. I have the action or reaction at that pinned hinge, A sub X and A sub Y. I have the weight downward, and there's one more that would be applied to it. It's sitting on some concrete slab, is it not? And so we would want to have, this was from the pin, A sub Y, but you also have some R pushing up on the bottom. Okay? One other thing that could be included, but there's no information given, is if this trough material, if it's empty, just by itself, no water in it, maybe that trough has weight, right? And if I wanted to include this trough material, the wall of the trough, right? What would I do, and where would I put it? I would say the wall has weight, just like the water has weight. So I'd say, okay, I'm going to introduce the wall weight instead of the water weight. And where would I put that on my free body diagram? From symmetry. Yeah, you'd put it right here in the middle. What would be that angle? 45 degrees. Well, they didn't give me anything about the weight of the wall, so I just talk about it, but I leave it out. Make sense? So I leave it out of the calculations. Now, I go ahead and I want to calculate magnitudes of f of r and w, because I don't really need to consider r, a sub x, and a sub y. If my goal is to calculate t, for this free body diagram, I'd employ the sum of the moments around point A. And the sum of the moments about point A must be equal to 0. Hence, I would be able to say f of r operating at, let's say, a radius divided by 3, 1/3 up, okay, from that point A. That makes it want to spin in the clockwise, or rotate in the clockwise direction, plus the weight. And that's at a distance, I'm going to leave it symbolically, f4r divided by 3 pi. We already know the magnitude. We already know the magnitude of this one. It's 0.2. We know the magnitude of this one. It's 0.254, whatever, 65. Okay. But I'm just doing it by equation. And then I have the tension as the only other thing. I'm going to put it back on this side of the equation. I'm going to say the tension times its moment arm distance. What is that distance? R. Isn't it R? And R is 0.6. So now I say, great, give me f of r. What is the resultant from the distributed load hydrostatic triangular shaped on that side? Is it going to be an average pressure, or the pressure at the centroid times the area? Is that the way we calculate it? And the pressure at the centroid, is that going to be the rho g h of the centroid? Sure. And this area, is that going to be r times, and now I haven't introduced a symbol for this 3 meter depth, but it's per every 3 meter depth. Let's not use W for the depth. You pick, you tell me, what symbol would you like to use for the depth? It's this 3 meters that we're trying to introduce a symbol for. This distance right there, right? Each cable has to support 3 meter depth of the trough. What symbol would you like? It's not a hard choice. C, he picks C. Well, I'm using C for center of gravity. Z, all right, Z. Okay, I like to reserve Z for sort of like elevation in the direction of gravity. Pick another one. No, D. D for distance, or D for depth, or something like that. I'm just playing with you a little bit, see if you're awake, right? Okay, now what we want to do is we want to substitute numbers to calculate this f of r and get a magnitudes, just like we have a magnitude for this distance, that distance. What's that f of r? It's going to be 9.81 kilonewton per meter cubed times h of c. H of c for this problem is, oops, clicker question. H of c for this problem, I have answer A, answer B, or answer C. Answer A says H of C is equal to 3 meters, equal to not 0.3, 0.4 meters, or 0.6 meters. So that's my 3 options for the magnitude of h of c. Is h of c 0.3 meters, 0.4 meters, 0.6 meters, or if you want a D option, D is none of the above. All right, everybody in, I hope. So, you didn't go fast enough? You only got 30 seconds for each one, all semester. So, 55% is right. True? So, have I warned you that every year that I've taught, I seem to get a consistent complaint? That's not a complaint, but maybe you say it's a complaint. The students say there's not enough partial credit. So I just warn you. I don't know if you've been in other engineering classes, you thought you aced the exam, you find out you made this mistake, this mistake, this mistake, this mistake, and your grade is a lot lower than the 100 that you anticipated. Anybody had that experience? I have as a student. So please, please, please work through the little details. That's why solving lots of problems helps you ace exams. All right, so why is it 0.3? It's not the centroid of the triangular pressure distribution. It's the centroid of the area in which the water is pushing against. And that water pushes against, it looks like a rectangular area of 0.6 and 3 meters. And so you put the centroid, it's 0.3 down. 0.3 down. The answer was A. Did that make sense? No? Okay, then I asked, how many questions have you solved since we last met? 20? And you still got that wrong?
I got it right.
Oh, you got it right.
I misread it though. I thought it was 0.2, to be honest with you. It didn't look like a 3.
But you still got it right? Yeah. Okay, sorry about that. You could stop me and say, is A 0.2 or 0.3? It looks like a 2, but you're saying 3. Then I'll clarify. All right. So this is 0.3 meters. What is R? 0.6 meters. What is D? 3 meters. Okay. And if you run that number, I think you get a 5.297 kilonewton. That's the resultant force due to the hydrostatic pressure on the side. Does that, anybody have a calculator? Does that?
That's right.
Thank you very much. Now, I'm going to run out of room. I tried not to run out of room, but I think I am. What about the weight? How do I calculate the weight? Yes? Well, what is rho? 1,000. So what is the kilo? 1,000. So I put it together. I put the rho g is 9.81 kilonewton per cubic meter. Yeah. Okay. What about the weight? Right. So you just kind of go slow. We know it's mg. Then I need the mass of the water. Okay. Well, the mass of the water is going to be the density times the volume of the water. Then I multiply that by g. Okay. So what is going to be the volume? I look at it and I say, I know the depth D, but I need that area. And then I push that area back a depth D. That gives me volume. The area of a quarter of a circle is 1/4 pi r squared. and I push it back a depth d. How many people like that for the volume of the water multiplied by rho g, you get the weight of the water? Good? Okay, we substitute numbers. Here's that. I'm going to substitute for the product, rho g, 9.81 kilonewton per cubic meter, times 1/4 r pi times 0.6 meter squared, times 3 meters. And I believe the weight comes in at 8.3211 kilonewton. Anybody verify that for me? 1 thumbs up, good. 2 thumbs up, 1 more thumbs up, and I'll be happy. 3, we're on. Thank you very much. So now you substitute our value for the weight, for the resultant force. We know what R is. Guess what? I'm just running out of room. The tension comes in at 5.30 kilonewton. Is that the right units for tension? Yes. Yeah. And that magnitude look good? How about you already verified the 5.3? Anybody else verify the 5.3? If you're running your calculator. I'll wait till I get 3 verifications. One is good. 2 is good. Looking for 1 more thumbs up. It says that you ran it and you got the same answer. That's my 3rd thumbs up. And we're going to press forward, okay? Look good? Any comments or questions on this problem?
Can you explain the height of the central one more time? How you got that 0.3?
I know I'm running out of room. Let me get rid of this. I try to look at this as a surface in which the water is pushing. And so I try to kind of look back at that surface. It's a radius r deep and depth d back. Now I say, what is the centroid of that area? It's kind of here pushing back a distance. And so it's easy that it's half foot away, so it's like a 1.5, such that the total length is 3 meters. And it's down halfway, 0.3, so it's at 0.3. In a few more years, people will be able to lecture and they'll have dynamic things that rotate. And it'll be so easy for students in a few more years to see things in 3D. Maybe. Maybe. Buoyancy. I think we've all experienced buoyancy physically. And so what is buoyancy? It's an upward directed force. And Archimedes came out with it, and so we have Archimedes' principle. Well, what exactly is Archimedes' principle state? It says that the buoyancy force is equal to something. What is the buoyancy force acting on a submerged object? I have an object right here. Think about a solid object. It's heavy. It's submerged. It's submerged in a fluid. What is the buoyancy force, the upward directed buoyancy force equal to? Archimedes' principle says it's equal to the weight of the volume of fluid displaced by the solid. It's the weight of the fluid that's displaced by the solid. Right? So let's go ahead and say, how do we derive this almost miraculous result? Well, take any solid, and think of it breaking it into itty-bitty little pencil-thin or even smaller than a pencil-thin cylinders. And that whole chunk of solid can be summed up by all these little pencil-thin cylinders, true? So if I can work it out for one little pencil-thin cylinder, then I can work it out by summing them all up. So if I look at a pencil-thin cylinder, okay, and it's in a fluid at rest, is the pressure of the fluid at the top higher than the pressure of the fluid at the bottom? Or are the pressures the same? It's in a fluid, it's in the presence of gravity. Is the pressure of the fluid at the top of this little pencil-thin cylinder higher or lower or the same as the pressure at the bottom? Good clicker question. Let's call this point A, call this point B. This is the answer. I say the pressure at A is equal to the pressure at B. That's, you would say, okay, answer A for the clicker question. Pressure at A is greater than the pressure at B. You answer answer B. Or the pressure at A is less than the pressure at B. You answer C. Or I have no idea. You can answer D or E in that case. Right?
It's completely submerged.
It's completely submerged.
And it's full of water?
It's fluid. I didn't say water. It's just submerged in a fluid, and the fluid is static. The object's not moving. The fluid's not moving. It's stagnant fluid, and the object's not floating up or sinking. It's just sitting there. You only have a few seconds. All right. So a lot of people say the pressure at the top is less than the pressure at the bottom. They're correct. Now, let's do this. What is the different, let's say this is the pressure A. What is the pressure at B equal to? Well, it's equal to the pressure at A plus rho times G times H, where H is this height of that little pencil-thin column. If I had a taller pencil-thin column, wouldn't it be a greater pressure difference? Yeah, it would be, true? Okay. So this pressure operates like a little distributed load on the bottom surface, pushing up on that little cylinder. And the pressure up here pushes down, true? True? Okay. Let's do this. The net force that the water or the fluid exerts on this little pencil-thin cylinder, if I know that there's force acting in the non-gravitational direction on the wall of the cylinder, but I'm really looking at it just on the two ends, the flat ends of that cylinder, okay? So the net force will be upward or downward directed that the water exerts. The top is lower pressure, the bottom is higher pressure. It will be upward directed, okay, on that cylinder. That net force due to the difference in the pressure on the fluid, okay? Well, it's going to be upward directed. Can you tell me the magnitude of it? Would it be the pressure at B minus the pressure at A times the little area of the cylinder? The little area that it operates on? Sure. And so this pressure difference, well, that's just going to be rho G H A. What again is A? What again is H? And how could I interpret the product of H times A? What is that equal to? That's the volume of my little cylinder, isn't it? Isn't that the volume of the cylinder? So what we have is we have that the upward directed force, let's call it the buoyancy force, due to the fluid on the outside of this object is equal to rho times G times V. What is that V? Velocity or volume? Sometimes we put a little thing like that, say, hey, this really, don't get confused. It's not it's a volume, not a velocity. Okay? That's not a new Greek symbol. It's just a volume with a little mark through it. Okay? All right. Let me ask another clicker question. Answer A, answer B. What is this row? Is this row right here? Is that the row of the fluid or the row of the solid? Okay, I have two substances. I have a solid or I have a fluid. What is that row? Now I started the clicker. You got 30 seconds. Is that row there the row of the fluid or is it the row solid that gives me the buoyancy force? The polling has stopped and we'll take a look at the results. And the reason I ask a question like this is I've been previously confused. Usually I ask a question about a point that I've been previously confused about. I may still be somewhat confused about it, but that's okay. But this is a tricky point. Isn't it the displaced fluid? So you think about it, I can interpret this if I take the rho and I multiply by V. You know what that really is? That's the mass. That's the mass of the fluid that is displaced. The volume of the solid occupies some volume. When it gets submerged, that fluid can't occupy that volume. This works for a little pencil-thin cylinder. And then you just sum it up for all the little pencil-thin cylinders that make up the solid, and you have the overall principle. It's the same, but that's the mass of the fluid that's displaced times G. And I know mass times G is weight. Is it the weight of the solid that displaces the fluid, or is it the weight of the fluid that is displaced by the solid? This is a tongue twister, but if we get the concept right, it's the weight of the fluid that's displaced by the solid. That's the magnitude of the buoyancy force. Let me ask you this. Is the buoyancy force, let me write that down, fluid, weight of the fluid that is displaced. Is the buoyancy force always upward directed? That's true. It's always upward directed. Okay? Now, where do you think the buoyancy force should be applied if I'm doing a free body diagram on this object that's submerged? At the C. What does C represent? The centroid of the volume that the solid occupies. True? So it's truly a centroid. The upward directed buoyancy force is applied at the centroid of the displaced fluid. Okay. Now they also show the weight. What is this weight being applied at the centroid? What does that represent? The weight of the solid. The weight of the solid. And that gets applied at the center of mass of the solid. Now, often our solids are uniform density. Rho is constant. What do you mean? Which rho? Rho of the solid is constant. That's often the case. But if we had a problem where the density of the solid was very high on this side, rho of the solid is very, very high on that side. And over here, it was very, very low. The rho of the solid is low on that side, lower than on the other side, right? We have more density, less density. What would change? Would the magnitude of the buoyancy force change? No, it wouldn't. Maybe I should have had a clicker question on that one, huh? Would the magnitude of the buoyancy force change? It only depends on the volume of the solid and the density of the fluid and G, or the weight of the fluid that's displaced, right? Okay, so it doesn't depend on if the density is non-uniform of the solid. Now, the second thing, does the location of the buoyancy force where it's applied in this volume, does that change? Thomas, you're so good to me. You give me wrong answers so often. You're learning too. I'm learning too. You know, it's okay. What about, where should I apply that buoyancy force? Should it always be at the centroid of the volume? Yeah, it should be. All right, now think about the weight. The weight, did that depend on the density of the solid? Okay, let me go back up here to fluid. The buoyancy force, did that depend on the density of the solid? No, you're getting better. You're getting really good. This is tricky. You've heard of Archimedes' principle so many times, right? You've even used it so many times. But you got to get it straight in your mind. That's true. The buoyancy force only depends on the fluid density, the volume of the solid, and G. True? All right. Now because the weight does depend on the density of the solid, for this case where I don't have uniform density, it's heavier or higher density on the left and lower density on the right. Will the correct placement of W change, or should W always still be at the centroid? It changes. Should it shift a little bit to the left or a little bit to the right? A little bit to the liberal, a little bit to the left. True? The weight's applied at the center of mass of the solid. True? Got it. All right. It's a simple principle. Now let's apply it to solve a problem. The density of a liquid is to be determined by using a 1 centimeter diameter cylindrical hygrometer. So I have some unknown fluid. I'm really looking to calculate the density of this unknown fluid, UNK or UK. What's a good symbol for unknown? Density unknown. Okay? I want to calculate it. This is a hygrometer. What's it look like? A test tube. All right. Probably glass filled. What's this down in the bottom of this test tube?
A cylinder and a half sphere.
Probably something heavy. Maybe put in a little mercury or some other object that's heavy in it, such that when you dunk that test tube into the water, it's going to stand up pretty straight. True? It's not going to easily tip and wobble a lot. It's going to stand up because there's the weight's down at the bottom. Got it? All right. Now, let's continue to read the problem. The hygrometer is first dropped in water. Oh, let's go over here and kind of sketch it where the hygrometer, here's my water. I drop in my hygrometer. Maybe what color do I want to put it? Black, I don't know. And so it goes down, down, down. And then I mark a level for the water. I get a little pencil out and I say, there it is. There's the level that the hygrometer sits in the water. Then I pick it up and I move it and I drop it into the other liquid. And the observed mark that the water had now has risen to 0.3 centimeters above the liquid air interface. Here's my red mark. That mark is now outside, above the level of the new fluid. Okay? So the height of the original water mark now is 12.3 centimeters from the bottom. You measure up. It's now, it used to be 12.3, now it's at 12.0. What am I writing? The height of the original mark is 12.3, right. Determine the density of the unknown liquid. How am I going to find that density of the unknown liquid from this information? Well, we will use Archimedes' principle. We just learned it. We're just going to apply the concept. And so somehow I have that the weight of this hygrometer hasn't changed depending on if I'm putting it in water or if I'm putting it in the unknown fluid. True? The weight has not changed. Has the weight of the hygrometer changed? Yes or no? No. All right. Thing about this, though, the buoyancy force that the hygrometer feels when it's put in water versus the buoyancy force when the hygrometer feels when it's put into the unknown fluid. Has that changed? Has the upward directed buoyancy force changed? Okay, let's do this. I want a very simple free body diagram. This always bothered me when I was teaching statics, right? All right, students, get ready. We're going into really tough stuff now. We're going into free body diagrams. They introduced the concept in the Hibbler textbook. Here's the chapter. Introduce free body diagrams. You know what? The whole chapter is the free body diagram goes down to a point. Looked like a free point diagram instead of a free body diagram. It wasn't until the next chapter that you were introduced to moments of forces, and then actually the body came into play. Look back at the book that you bought and you used for statics and check me on that. So here's my great free point diagram, my free body diagram. I'm going to have a buoyancy force pushing up. I'm going to have the weight of the object pulling down. I'm going to do this 2 times. I'm going to do this for the case of the water, and I'm going to do this for the unknown fluid case. Did I get my free body diagrams correct? For 2 cases. All right, now the question is we just said the weight of the hygrometer didn't change. And then I asked the next question, did the upward directed buoyancy force between the 2 cases, one in water, one in the unknown fluid, did that change? All right, we have clicker question time. So A, the force, upward directed buoyancy has changed. Or B, the upward directed buoyancy force is the same. It's the same. Okay, now we start. Here we go. All right. Now we have, before I answer the question, because I hate to do this, I have to think about how I'm going to answer this question to be helpful, right? All right, if I look at this free body diagram on this side, what can I conclude about the relationship between W and F of B in the water? Is it greater, equal, or less? Equal. Okay. You're pretty you got it. You got it pretty fast there, right? So I conclude that that's true. How about I analyze this system over here? Is W greater than, equal to, or less than the buoyancy force in the unknown fluid? Hey, you did that too fast. Are you sure about it? Is it equal? Yeah, it's equal. So, if W equals W, and W equals F of B unknown, and W equals F of B known, or water, guess what? All right, let me continue on and maybe you'll back up and see why that's correct. But let's do this. Let's go here and say, now that I know that the buoyancy force in water is equal to the buoyancy force in the unknown fluid, then I say, well, what is the buoyancy force in water? Is it going to be the weight of the water displaced? Yes. what equation would I like to put in for that? I'll put in the density of the water, I'll put in the volume that the water displaced, and then I'll put in G. And then I'll come over here and I'll say, would that similar equation work? The density unknown fluid, that's what I'm trying to calculate, times the volume displaced by the that the hygrometer displaces of the unknown fluid, times G. Can I cancel the G's? Can I cancel the rho's? No. No. Can I cancel the volumes? No. No, no, no. So I say, okay, I know that I have to figure out this relationship, but the volume unknown, let me ask you this. The volume unknown versus the volume when it's put in water, right? When I put the hygrometer in one of the fluids, it displaces more volume than the other case. So the volume of fluid displaced, is it greater, equal, or less? I'm going to answer question A, B, or C. Volume of the fluid that the hygrometer displaces of the fluid. All right. There's still a lot of distribution. Well, again, this notation is this is the volume. Volume of what? That's the volume of the fluid that's displaced by the same hygrometer when it's dropped in the unknown fluid versus when it's dropped into the water as the reference. When it's dropped in the water, didn't it sink further? Didn't it sink further? So wouldn't it have displaced more fluid? So the volume of the fluid displaced when the same hygrometer is dropped in water is greater than the volume that the same hygrometer displaces of the fluid when it's dropped in the unknown fluid, right? Very good. So answer was C is correct, true? What is this volume for the displaced water? Well, I'd say it's something like this, roughly. Probably some pi d squared over 4, where this is some diameter, times some height. And I would say that height is 12.3 centimeters. I know that this should be a little box down here and there's a little curve, but I'm not going to worry about that little curve, okay? So it's around the area pi d squared over 4 times 12.3 centimeters. How about the volume in the unknown? Pi d squared over 4 times 12 centimeters, true? Okay, so at this point I can write, I've already graded that, so I can write the equation that I'm looking for. The density of the unknown fluid is equal to the density of water times the volume displaced by the hygrometer in the water divided by the volume displaced by the unknown fluid. It's rho of the water. The pi d squareds over 4 cancel. Let me just write them both. And then I'll have the 12.3 divided by the 12. So the areas cancel. And so what value do you think I want to put in there for water? 1,000. 1,000. I know it's not perfectly 1,000. You got to tell me the temperature, professor, because I know density of water changes slightly. And oh, by the way, is it atmospheric pressure, 5 atm or 20 atm? You know, okay, yeah. But put in 1,000. There you go. So the density of the unknown fluid comes in at 1025 kilogram per meter cubed. The specific gravity of the fluid is 1.025. It's slightly more dense. True? Slightly more dense. Make sense? I'm sorry that took so much time. I hope I cover as much material as I want to today. Any other questions? Ready to press forward? Okay, now we want to talk about fluids in rigid body motion. The fluid's not shearing. The fluid's not turning around and moving and all that. It's just, but it's in motion. Let's do this. Let's take a cup of water. There's the water. And I'm going to start at rest. I start at rest. And I say to myself, this same cup of water, it's not accelerating, it's sitting on a table, the acceleration is equal to 0. Is there a difference in the pressure between the top and the bottom of the water? Is there a delta P between the top of the water and the bottom of the water?
Yes.
And what is that equation from memory? Rho GH, I know the H, and I know G, the gravitational field. I have it on the surface of the Earth. Great. Do this. Somehow I figure out that I can take the same exact cup of water and I'm going to put it in an elevator that's like a skyrocketing elevator, and it's only for a few seconds it's going to start to accelerate me to get to the top of a tall building, I don't know, the Tower of Americas. You ever been in an elevator and it starts off and it's like, you feel heavier, maybe your knees want to buckle or anything? Okay. While you're doing that, let's say it's experiencing an upward directed acceleration. A in the z direction, here's the positive z direction, is greater than 0. This ace of z was 0. It is sitting stationary on the table. It's not accelerating in the first case. The second case, I'm in an elevator and it's accelerating. Or put me in an aircraft. I know that we have to be in a military aircraft, but you could take that military aircraft, point it straight up. They're so powerful, some of these jet engines, jet aircraft, and you can accelerate vertically. What? Oh, yeah. Oh, yeah. You can accelerate vertically. So now you're a pilot. Now you have to tilt the cup from when you were just flying horizontal, because now you're flying vertically. And you're still holding your cup. And that's the cup of interest. The cup didn't expand out and all that. The water's at the same height, isn't it? In the elevator or in the jet aircraft. But answer this question. The pressure difference. Did it go up? Did it go down? Did it stay the same? Tell me a little bit about that delta P. Clicker question. Oh, man. I don't know if I got time for any more clicker questions.
Pressure difference stays the same, or
Yeah, the delta P. We already said the delta P was rho GH. This is H. The H is the H going to change? Is the H going to change? The cup doesn't expand. Is the H going to change? No, it's incompressible. So is the delta P going to change? The pressure difference between the top of the cup and the bottom of the cup? The air pressure in the cabin, the air pressure, in the elevator, I don't feel like, I can't breathe because the air pressure went up or something. No. Or it went all the way, right? The air pressure is atmospheric pressure. Did the delta P change? All right, we have another case. We have the cup. And this is the dread of every person that's ever ridden in any elevator. What happens? The cable breaks. And now you're in a free fall. Oh, it's fun for the first few seconds. But there's something at the bottom of that free fall that's going to... But let's not get there. You're now free falling with that cup of liquid and you're just holding it. You just paid a lot of money for it and you're just holding it. Now you're free falling, right? Is there a difference between the pressure at the top and the bottom of the cup of liquid? Well, let me do this to help us develop the mathematical rigor in which we can now explore some of these concepts. Let's do this. We'll introduce a coordinate system. And we'll introduce this coordinate system. We're really interested in Z for right now. Okay? So I'm going to put the X out here and the Y over there. And I'm going to put a little control X. And I'm going to think about analyzing this system. Actually, let me stay with this one. Put the X here and the Y going backwards so it's still a right-handed coordinate system. Now I have X, Y, Z, and I'm really interested in a little chunk like that. The little chunk I pull out and I look, it starts at X and it goes to X plus delta X. It starts at Z and it goes to Z plus delta Z. True? All right, I have it. The chunk of fluid that I'm looking at surrounded by its neighboring chunks of fluid. So each chunk of fluid on the outside pushes inward. It always pushes inward. The neighbors always push inward on the chunk of fluid of interest. Pushes, 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 pressure, 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 pressure. I want to do a sum of the forces equal to the mass times acceleration, Newton's second law, to this little chunk of fluid. I know it's at rest, but we're going to start playing with it in a minute. So what would be if I'm looking at the z direction? Z direction. Well, I'd say the pressure on the bottom is pushing up. That's pressure at z. Times the area. The area looks like it's a delta x, delta y area. And then the pressure at the top is pushing down, z plus delta z. And it's pushing on an area delta x, delta y. Those are my two surface forces acting in the z direction on this little chunk. Got it? But I don't only look, when I'm doing dynamics problems, I don't only look for surface forces, I also look for body forces, things that happen inside because it has some mass inside. What is the body force of interest? It's got a little W. A little W. What is the weight? Well, the weight is going to be minus, I need to write it down here, I'm going to run out of room, minus, because it's in the negative z direction, going to be the mass, which is the mass density times the volume, delta x, delta y, delta z, times g. Isn't that the weight of a little chunk? Density times its volume. The volume is delta x, delta y, delta z, times g is its weight. True or false? I didn't say go to sleep on me. I said stay with me. I got to do a little derivation so we can take the math that we build and then apply it and answer these questions correctly. And then answer more challenging questions. That's equal to m times a. True or false? Sum of the force is equal to m times a. Newton's second law. But what is the m? Isn't that rho times delta x, delta y, delta z? Isn't that the same m as what I just put? Yeah. And then if it's undergoing acceleration, if that little chunk of fluid is accelerating, then that a is non-zero. For the first case up here, guess what a was? 0. Right? In the second case, guess what a was? Greater than 0, a sub z. And in the third case, a sub z was less than 0. Because it was, but let's not get ahead of ourselves. I have this equation. I take each of those terms, and guess what? I divide by delta x, delta y, delta z, divide by delta x, delta y, delta z, divide by delta x, delta y, delta z. I cancel, 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 cancel. But I left with this very funny term, which is p sub z plus delta z minus p of z divided by delta z, and I'm going to put a negative sign because I need to do that. Then I have a minus a rho g equal to rho a. Did I do that correctly? Good. This is only in the z direction. What do I do with this quotient right here? Well, I do this. I recall from, what is that word? Oh, that word I wanted to avoid after I passed that class. I never wanted to see it again. All right, you're a true engineer, not a mathematician masquerading as an engineer. Right? But here it is. We go back and we have f at x plus delta x minus f of x divided by delta x. And I take the limit as delta x goes to 0 of this quotient. I ask the question, clicker question, answer A or answer B. This limit of this quotient is either something or it goes to infinity. You're all budding mathematicians, or at least you passed those classes, you know what I mean? Here I have this quotient, f of x plus delta x minus f of x. What's f stand for? Function. I divide it by delta x. I let the delta x go to 0. It's equal to something, or it goes off to infinity. All right. I need to apply that concept so that I can go from here to here. And I need that differential equation. I do. So now what I can do is I can plop this term over on the other side. And I really don't like the minus sign there. I hate doing that. Let me clean it up and take an extra step. Let me try and rewrite that equation up here. It's going to be dp dz equal to minus rho times a sub z plus g. True? You know, I could take that equation for the first case where a sub z is 0. Should I move to another page or try and reuse this one? Reuse it, stay on the same page. If a sub z is 0, then my equation becomes dp dz is equal to minus rho g. Can I separate and integrate? Simplest ODE you ever wanted. Isn't it? And so I separate, integrate, I get p at z minus p naught equal to minus rho gz. And so I start my coordinate system at z, 0. I move up, 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 up. As I move with increasing z, I've left off the z right there. No, I put it right below. Right there is my answer. What happens? The pressure goes down as I go up higher and higher in the fluid, in a stagnant fluid. True or false? True. So that confirms what we just said. We start here, we go down, it goes higher, increases pressure, etc. Now let's apply it for this other case. A sub z is greater than 0. I know I've never been in a military aircraft where I'm being accelerated vertically going up. But I've been in an elevator and I tried to describe how my knees sometimes felt the extra weight of my body, like I felt like buckling a little bit. If I stood on a scale, maybe my weight would be 190. Put it on the elevator. Watch the dial as I go accelerating up in the elevator. Is it going to go down? Is my weight going to go down? Stay 190 or go up? Go up. Hey, did I mention that dynamics is a prerequisite to this class? That means you must have passed dynamics, EGR 2513 with the letter grade C- or better. If anybody is in this class and they have not done that, they need to see me or just kind of drop quietly. Withdraw quietly, okay, please? You cannot be in this class without the prereqs, right? So that's one of these concepts from dynamics, right? True? My weight's going to go up if I'm... Now, unfortunately, my nightmare happens. The cable breaks. I start to fall. What's my weight on the scale going to show? 0. That doesn't happen, and engineers have designed elevators. Don't have a nightmare tonight. That when they have fault, there's backup mechanisms and everything else, and it won't fall like that. It's only in horror movies and in your dreams, my nightmares, right? All right. Now, you go to this case. Guess what? The world turns around. If you're free falling, hold it. If I let this free fall, right? This sitting, it just sits. This is accelerating upward. The second case. The last case is free falling. A sub z, if I just let it go, does my water in that cup accelerate? Yeah, it accelerates with a negative g. It accelerates with a negative g. So when I come over to this equation, dp dz, the change in pressure with depth, minus rho times a sub z plus g. And if a sub z is negative g, guess what? And the pressure difference is 0. The pressure is the same as the top and the bottom in my cup of water as I'm free falling. True? Wow, that was a tough introduction because we have some tough concepts to now get into. But let's press forward. I need to talk about now not just linear rotation. Let's do this one. If I have a tank of water right here, there's my fluid level, and now I don't accelerate in the z upward or decelerate in the z or whatever. I'm doing this in the x. Now I have to get an equation which works in the x as well as the z for how the pressure changes. Well, how do I want to handle this? Let me try the physical approach. Let's say I put this on a truck or a car. Let's say I have this cup of water. I'm in a car. I'm at rest. The light turns green. I have a sports car. I love the exhilarating feeling of accelerating away from the red light. It turns green. I like to go, right? Through the intersection on. I don't know why that excites so many people, but it does. And so when it does, and I'm accelerating in that direction, what does the water level in the cup that I hold horizontal do? It shifts. And does it shift this way or the other way? That way. That's the way it shifts, okay? Now, I'm holding it there for a second. It's hard for my car to continue constant acceleration for a very long time, right? But I'm holding it there just long enough. It's accelerating, constant accelerating. The water is shifted. What is the difference in the pressure anywhere along these points that I've just shown? Is the pressure the same along that line? It's all atmospheric pressure. Let's say I take a look at the pressure there, along that line, a parallel line, but now it's completely in the fluid. It's not at the air-water interface. It's the same pressure, right? So our lines of pressure have changed. Where is the highest pressure of the water in the container? In the corner. Right there in the corner. Right there's the highest pressure. True? Okay. So what we can do is we can relate the angle. Let me try and draw this angle here, phi. Somehow I can get a relationship between that angle phi and my accelerations. What I have is I have an a sub x positive in the x direction, and I really don't have an acceleration unless I drop it, but I'll call it g downward. True? Right? I mean, if a sub x could be, g, let's say g is 10 meters per second squared. If a sub x could be 1,000 meters per second squared, what do you think the water level in the cup would look like? It would almost be like here's the cup and here's the water. True? All right. So how about if a sub x is, 1 meter per second squared? Well, it's still primarily g is 10 and a sub x is 1, so it's going to have some modest slope. True? True? What is that relationship? Some tangent, of course. Sometimes engineers just work it out because it's got to be there, right? It's like, I know that the solution looks like this. It's going to have the tangent function in it somehow. True? So the tangent of phi is going to be a relationship of something, guess, a sub x divided by g. Let me ask you this. If I put a sub x to be 0, what is phi? Arctangent of 0. Hey, I got a calculator. What is the arctangent of 0? Somebody want to confirm that with me? No, I don't have a calculator. It's 0. Wouldn't that work? Wouldn't that work? So basically, as a sub x increases, phi, let's put in 1 meter per second squared divided by, now let's put in 10 meters per second squared. And then we'll do the inverse tan, right? Arctan of 1/10. What is the arctan of 1/10? All right, let's. We have an answer of 5.71. Anybody else? Yes, sir. You got to confirm. Is your calculator in radian mode or degree mode? It's in degree mode. So this is an angle of 5.71 degrees. Visibly, does it look like I exaggerated too much phi? Or does phi graphically look, oh yeah, that looks like about 5.71 degrees? Yeah, because this is 90, that's 45. I look at 20, 25 or something. So I've grossly exaggerated phi in the illustration. It's much greater than 5.71 degrees. So there it is. Now, how do I back up and do this mathematically? I don't have time. I need to move on. But I shouldn't do that. I should give you the mathematical rigor. I'm in a perplexing situation here. Well, we know that it's as if this is the negative g right there in, this direction. And then we have that direction. So it's like negative g. And this is a sub x. And so we come out like that. And that is perpendicular. That's perpendicular right there. All right? So the resultant net acceleration, the combination of the weight, I know it's not free falling, so it's, and then the actual acceleration to the horizontal, give me that you have a perpendicular force. All right, I'm going to let it go. Perpendicular angle. One other case that I need to cover is not only do we sometimes go linearly up or down or sideways, but we may have a system where you have a cylinder and a center line through that cylinder. And we rotate that cylinder around the center line with a speed of rotation, omega. This omega could be represented in hertz, cycle per second, could be represented in RPM, revolution per minute. But often we've got to convert those to something in radian per second. You familiar with the radian? Radian. How many radians in a whole revolution? 2 pi. Professor, do I need to memorize that? Yes, you do. All right, so there you go. Now, so here is my omega. You're rotating it. Before I started rotating it, my fluid level was straight across. Got it? I start to rotate. Clicker question. Clicker question here. The fluid level will either, answer A, stay level, or B, develop a shape where I'm just kind of sketch it. I'm going to say this is the center line, and the shape is higher on the outside and lowest in the middle. That's answer B. Or C, that the shape is such that there's the center line, it's highest in the middle and lowest on the outside. Does the level of the fluid in the tank, after a long time, it's in rigid body motion. I know that if I start the outside fast, the inside will take a while to catch up. But it's waited a while and it's all caught up. At that point, does the fluid level, if I look inside the tank, is it still flat? Is it level? Answer A. Is it low in the middle and high on the edges? Answer B. Is it high in the middle and low on the edges? Answer C. You think students either gave up on me and nobody's answering anymore, or you're really getting smart. And there's 46 people. That's hard to get 46 people to answer, yes, this is the correct answer. Not bad. I asked that same question this morning, and it was not 100%.
That should be evident of the earlier you get up, the harder it is.
To think straight?
Yes, sir.
Well, actually, most of America still gets up at 8 a.m., and that's the work day when it starts. And a lot of companies, there's a lot of engineers in early before 8 a.m. So I think if you just shifted it, if everybody said, okay, we're going to work from 9 to 6, after a couple more years, you know what people would say? 9's too early. Okay, we'll go 10 to 7. 10's too early. 11 to 8 p.m. You got to wake up sometime. It's a product of when you go to bed, isn't it? That's what I tell my children. They're like, look it, son, if you go to bed at 3 a.m., it's pretty hard to get up at... All right. So this thing diverges. Now, if I take a look at looking down on a cylinder, and let's just study one chunk of fluid right here. And the chunk of fluid is going along in a path. How would we describe that path of that chunk of fluid? It's going in a circle. It's going in a circular motion. About a center, here's that center line as a dot. Okay? Now, this always throws people for a loop when they took dynamics. You have a chunk of mass, and it's rotating at constant speed omega. I'm not changing omega. Omega is a constant. It's not equal to 0. It's a positive number above 0. It's rotating, but it's a constant. And so there's something called the speed of that chunk of fluid. And that speed of the chunk of fluid is or is not changing with time. Is the speed of the chunk of fluid changing with time or not changing with time? It's not. Is the velocity of that chunk of fluid changing with time? Yes. So now, is that fluid experiencing any acceleration? Is the fluid, I'm going to ask a clicker question. Yes, it's being accelerated, or no, it's not being accelerated. Answer A or answer B? You're following. You learned something in dynamics. But do you have your clicker? No, I said accelerating. Is it accelerating? So most of us said, yes, it is accelerating. So it's always being accelerated inward direction. Always accelerating inwardly. What that does is it doesn't change the tangential speed because it's always perpendicular to the tangential speed, the direction of acceleration. It just changes the velocity, the direction. So, yes, it's being accelerated. True? If I have a chunk of mass m, I'm just now thinking back to dynamics. What is the relationship between some force needing to be pulling it inward directed at all times to continue its constant acceleration, not acceleration, constant omega, constant rate of rotation. So what is that force needed, or tension if you want to think of it as a string? Force is proportional to the chunk of fluid's mass, or chunk of solid's mass that's going around in that circular pattern, times what? I know, but what is the equation for the acceleration? I know it's acceleration, but what is that equation? The v squared over r, where r is the radius. Okay. Is there another way of expressing that? What is the relationship between omega and v? Is that the relationship? Okay. So could I put this as mass omega squared r? True. And that force is always pulling to the middle. So it's like it's having an F equal ma or the acceleration is negative r omega squared. True or false? Do you like that? Negative r omega squared? So what we have is when we have a cylindrical system, solid body, a fluid and solid body rotation, we like to adopt the coordinate system r and z. And there is an acceleration in the negative r direction, which is negative cap r, the radius, times omega squared. Or if you want to know the acceleration at this point, I need to put in lowercase r as to the radius, the distance from the center line to that point in the fluid. True? So maybe I want to put lowercase r right there. Right. So what we can do is we can get an expression for the pressure in the fluid. We already mentioned that the pressure contour looks like this. So anywhere along this line, is the pressure the same? And if I drop down, is the pressure the same anywhere along that line? And then, yeah, it's got a parabolic shape, a quadratic shape to it. And so what we have is we have that the pressure as a function of r and z. Let me see if I can draw this out. Oh boy. Because what we have is the change in the pressure with respect to r is equal to the density per unit volume, or the mass density, times r times omega squared. And we still have dp dz equal to minus rho g. All right? So if you separate and integrate this term, you get that P is equal to some P naught minus rho GZ, GZ plus any function of R. And then over here, what do we get? Separate, integrate, you get rho omega squared 1/2 r squared is P, the minus P naught, plus any function of Z. You combine them, you get P is equal to P naught, and then you get minus rho GZ, meaning if I move up in elevation, it's going to go down. And then I have 1/2 rho omega squared r squared, meaning that if I go out further in the radius, the pressure goes up. True? All right. So a line of constant pressure would have r is a quadratic. And so you can get the elevation of a surface z is equal to omega squared r squared divided by 2g. Then you have plus some height in the center. And so z is a function of r going out. It would increase. If you wanted to find z maximum, it would be cap r instead of lowercase r. So that's the pressure variation. We can use that to solve for some problems. Let's take a look at this problem. We have a 1.2 meter diameter, 3 meter high, sealed vertical cylinder. So it's a cylinder filled with fluid gasoline that has this density, 740 kilograms per cubic meter. The cylinder's filled with the fluid. So even though I start spinning it, I'm not going to develop a change in the interface between any air. There's a solid surface at the top and bottom of that cylinder that seals it. The tank is rotated around the vertical axis at a rate of 70 revolutions per minute. Determine the difference between the pressures at the centers of the bottom and the top surfaces. So along the center line, go from the bottom to the top. Let's call this point A. Let's call this point B. Which pressure is higher, point A or point B? Point A. Point A is higher pressure. So pressure at A minus the pressure at B is the pressure difference of interest. How do I solve for it? Let me do this. I'm going to pause for a minute, stop the recording. I'll walk around a little bit and see how you do on a piece of paper and pencil. All right, so let me back up a little bit. We have just developed the governing differential equations for how the pressure changes in the R direction and in the Z direction. Then we actually solved for the equation like this. P is equal to some pressure at the center at some reference elevation. Z is equal to plus rho omega squared R squared. Did I have that 2 in there? I needed 2. Did I have it? Where did I have it? No, I had it in there. Where is it at? Right there. I had the 2 in there, correct? So I had it in there. Sometimes I think, oops, did I leave a factor out in the solution? And then you have the change, which is a minus rho g z. True? That's one way of writing that equation. But you could also go back and write it this way. We have a pressure at state 2 minus the pressure at state 1, where state 2 is given by a Z1 and an R1, and it's 2 by a Z2 and an R2. And you find that that gets rid of that P naught, and you get that the rho omega squared over 2 times the R2 squared minus R1 squared. Did the radius change? If the radius changed in a rotating system, then the pressure is going to be different because of that centripetal force, okay, pushing it out, minus rho g Z2 minus Z1. What's that? The change in elevation. Did the elevation change? Did the depth in the fluid change? If it didn't change, then that's not going to contribute. But if the Z did change. So for the first part, for part A, I'm looking at this point. What is, let's say, that's at Z equal to 0 and R equal to 0. This is at Z equal to 3 meters, R equal to 0. So the pressure difference for part A is only due to the rho g delta Z. So Z2 or Z1, it's going to be, I'll represent the pressure difference as a positive amount, knowing that the pressure is higher at the bottom. And this is going to be 3 meters. So what's 9.81 times 3? Around 21.7 kilopascal. What is rho g? Oh, I've got to do this slowly. 7. You could do this way. You could put the specific gravity of 0.74 times 9.81 kilonewtons per meter cubed times the 3 meters, and away you go. There's a couple ways. But if people do it correctly, do you get 21.7 kilopascal? 1 confirmation, 2, 3, 4. Look good? 21.8, so 21.7. There you go. Now, you use the same equation for the second part, which says the difference in the pressure between the center and the edge at the bottom surface. So maybe I should have drawn A right there where the center line goes through the A, and then we just go out radius out here to point C. So at point C, Z is equal to cap R, which is 0.6 meter, right? The diameter is 1.2. The radius is 0.6. And what did I draw there? That's some people look at me like I'm crazy. The radius is 0.6 and the elevation is 0. So the change in the pressure for part B is going to be equal to 1/2 rho omega squared cap r squared. Let's chase the units on this one. 1/2 740 kilogram per meter cubed times, now we have to get that omega. I know it's given as 70 revolution. Well, every revolution is 2 pi radian. So 70 times 2 pi. But it's per minute. Well, every minute is 60 seconds. So 70 RPM is equal to 70 times 2 pi divided by 60 radians per second. That is omega square it. And we have r, the radius of 0.6 meters squared. Now, I only have this meter, a kilogram, and meter cubed. So we have to do our units carefully. Let's go ahead and do it. So Newton is a kilogram meter per second squared. That'll get rid of this kilogram per second squared. And then it'll get rid of one of the meters. It's hard to show canceling units because I don't want to mess up my square and forget it when I do 0.6 squared. And then I have also another unit conversion that I need is a Pascal is a Newton per meter squared. True? And kilo is 1,000. So that'll work for all my units. So the change in the pressure, what do you get for the change in the pressure? Anybody run that? There wouldn't be a free surface of constant pressure. What you would do is if you wanted to plot a surface of constant pressure, where would the very lowest pressure be? In the middle at the top. And then the lines of constant pressure would kind of go like this, then this, then this, then this, then this. And where would be the highest of the high pressures? In the corner, outer corner of the bottom. The outer corner, outer edge of the bottom, right? Maybe I should try and draw it symmetric about the center line and draw it like this. And this would be really low pressure. And then you have lines of constant pressure which still have that parabolic shape. And right there's the maximum pressure. But I have the free surface with the air because it's contained. Well, I wish I could solve some more problems, but I'm out of time. And so what I'll do is this. I'll talk about an exam.